Okay, I posted the most up-to-date current standing in this class for you. About an hour ago, I got the assignment 3 grades back from the TA, so those are included. So it looks much better now. So the way to read this spreadsheet would be the term mark is all the marks up to the final. Final would be about 35%. The remaining would be what I would classify as a term mark. So it's a weighted average of everything that goes towards the term mark. Right now, it includes the 3 assignments and 1 midterm. Okay, and I scaled it up to 100% so that you get a percentage. And what you see here is on the dark green above, those are marks that are 1 standard deviation above the mean for the term. Okay, and so that's, to me, roughly in the A territory. If you're in that pool, 1 standard deviation away from the mean above, then you're most likely to get an A if you maintain that. Okay. And then there is next range, which is in light green color filled, and those are all 76.3 and above, up to 1 standard deviation. That's a fairly large group there, and those would be, to me, most likely to get a B if you maintain that level of performance. Okay, and then below the standard deviation, that's in the red, all the way to 1 standard deviation below. Okay, that would be roughly in the C territory if you are in there. So this is just a feedback for you so that you can put more effort and move yourself from one range to another range. Okay, and those that are in filled kind of pink color, they are 1 standard deviation below the mean. Okay, and I would classify right now tentatively as a D territory, but I typically tend to be a bit lenient than this. I won't give as many Ds. But if you are at the very bottom, you have to put in more effort. There is one strong correlation that you can see in this. What is that correlation? If you did not submit any of the assignment, those are all in red. You get a 0 for the assignment. Okay, so these assignments do carry some weight. 20% of the weight is assigned to these. Okay, so if you skip 1 or 2 assignment, it's going to push you automatically to the bottom of the pile. Okay, and I was concerned, and one of the statistics that you should see here is the number of people who did not submit. The first assignment, it was 4. That line is here. Okay, the next one, it was 6. The last assignment, it was 16. 16 people didn't submit. Maybe you're already making up your mind that you want to exit this class, I don't know. But most of the people showed up for the midterm. Okay, but you can see there is strong correlation, all the reds against that bottom section. So that's one of the reasons why I gave an extension for this current assignment, because yesterday I had a lot of traffic through my office for the first time in this course. Okay, and I get a sense that people are struggling with assignment 4, and I don't want you to give up. Okay, so, but that doesn't mean you just push it aside and study organic chemistry or something else and then come next Monday and struggle. Okay, you should balance your time. You should put some effort in this course, particularly you are in the bottom section of the course. You should put more effort if you want to get yourself out of it, or I guess make alternate plans to take it against sometime in the future. Okay, so this is just a feedback for you, what it takes, and I see the class population also thinning down. I don't know what it means. I marked the exam myself because I wanted to get a sense of how the students are doing, and the sense that I get is there are probably 60–70% of the class that's doing very well. If you did all the assignment, you understood it, okay, then you don't have any problem with the exam. You do it very well. And then I think there's no problem. You'll say through this course. But there are a few at the bottom, maybe 20% or so, that do not have any clue as to what is happening. And if you are in that category, if you need additional help, you have to come and see me. Okay? I can guide you to do more, read more, work more. So that's a decision for you to make right now before it's too late. Okay? Otherwise, the only option would be to exit this course before the drop time. Okay? So, are there any questions, comments, feedback for me? I keep asking this question, how is the course going for you? And I get a silence. I don't know what to make of it. Yeah?
Can you post when you're available instead of when you're busy? Like,
Well, I have set aside Friday afternoons for this course, and I'm willing to open up, because the assignments are typically due on Tuesday. I find Monday afternoon there is a lot of traffic. Yesterday I was in my office and there was a lot of traffic. So I could open up. But my advice to you is, if I'm not busy, and if I'm in my office, it's open. You can drop in anytime. Unfortunately, this term I have a few travels. Okay, so again, end of this month in October, I'll be away for 4 or 5 days. And November, I'll be away for 4 days, but that happens to be Thanksgiving holiday, so that's not a problem. I'm going to University of Calgary at that time. It's not Thanksgiving for them. So, but other than that, if I'm not busy in my calendar, you can drop in. Feel free to drop into my office. If you want to make sure that I'm available for you, because open hours, you may drop in and somebody else is in my office, I'm trying to help them, then you may have to wait for a few minutes. Okay? But if you want exclusive time, then email me. I will say, okay, this time is for you, and I will be available for you anytime that I'm free. Okay? Is that a problem? Access to me is a problem. How many of you feel that you're not able to access me and that's hindering your learning? Don't be shy, because I need to know and I need to make alternate arrangements. If I'm not available, somebody else. You have had the problem. I think we have had once. You came to see me and I was tied up at the time. How many of you have made an attempt to come and see me and I was not available? Okay, if large number of hands go up, then I will make some arrangement. In the past, I made myself available on weekends through internet. Okay, so I'll be in my office or home, and we can access, you can reach me through something called a virtual classroom. I like playing with technology, so it has worked effectively in the past. Last year, we had it for 2176. Or I can, if necessary, I can come to the office and make myself available over the weekend.
Are you in the office on Saturdays?
I'm not usually in my office, but in a virtual office, meaning I'm at home working on my, and I have a home office, I'm working there, so I can open up a virtual classroom, which will basically mean there is a link on the Moodle page called the virtual classroom. So we have to agree, okay, we're going to be there on Saturday 10 to 12, and I'll be there. Any student can click at that link and you'll be connected to that virtual classroom. And then we will have chat ability, video, voice ability, and sharing of the screen. So if you're struggling with a program, you can say, okay, you give control of your screen, I can look at it, I can see where the problem is. So it's particularly for software stuff, it's a very good environment. Okay, any other questions, comments? What is your feeling on assignment number 4? How many of you have finished it? I'm glad that I extended it. Otherwise, this number from 4 to 6 to 16, it would have shot up to 64. Please don't give up. Okay? If you need help, tell me, and I will make myself available somehow. Okay? And those who have come, you can decide whether it has been useful to you or not. I hope it has been useful. But I'm seeing very few people. Of the 90 people, I've probably seen maybe 10 so far. Okay? And others, if you're doing well, there's no problem. Okay? As I said, in the top, those who are in the A category, you guys are doing well. If you don't need me, that's fine. Okay? But those who need help, you must make the initial effort to come and see me. Now, what I'm going to do today is kind of digress a little bit and prepare you for doing assignment 4. Okay? So I'm going to take one of the problems from assignment and a variation on the problem. And this is the kind of variation that you can expect in an exam. Okay? In fact, exam 1, I thought was very easy if we had done assignment 3. Right? And those 16 who didn't submit assignment 3 obviously would have found the exam difficult because we hadn't spent the time to go through it. So the exams would typically be a blend of these assignments, variation on these, and blend of what we have seen in the class. The second exam will involve more of function writing and debugging the function, finding the errors in the function, things of that nature. Okay, so let me, it's this one. In the last lecture, we saw what a function is, and I think those who came to see me yesterday have a good idea of how to write the function. The problem I noticed was how to use the function. Okay, once you write it, how do you use it? So today I'm going to talk about how to call function, how to track the execution of function, what is the difference between a function file and a script file, how do you capture this in a diary file. We will demonstrate all these things, okay? And then what is debugging? How do you debug? And how do you determine what is a local variable and a global variable? These are the agenda, okay? So it's going to be slightly deviating from what I was solving in the last class. We haven't completed that problem, and we'll go back to that problem probably in the next lecture to show you how to make the problem a bit more general and a bit more complicated to answer more general varieties of questions. That was a reactor temperature data that was coming from a plant, and we were trying to analyze that, okay? But we'll get back to that. The problem that I want to talk today is the distillation column. So let me just tell you a little bit about what that problem is, okay? And you will see this more in a unit operations course. And it is a unit that's available, used in most gas processing plants and refineries. What you have is a feed stream that is fed into a flash drum. Okay? The feed stream will have a certain flow rate and certain compositions. This could be ethane, propane, butane, pentane, hexane. Okay? Let's just take it as C3, C4, C5, C6, C7, 5-component system. Okay? Methane, we don't have propane, butane, pentane, hexane, heptane. A mixture of natural hydrocarbons that appears in natural gas or crude oil. And you control the temperature and pressure of the flash drum so that some of this feed goes to the vapor and some of it comes out as a liquid at different compositions from the feed. So the vapor composition, we will label it as YI, and the liquid composition, we will label it as XI. Our job is to develop an equation, which I'm not going to do in this course. You will do as a chemical engineer in a separation process course. But I'm giving you the underlying idea so that you get motivated why this problem is important, and then we will see how to solve this problem using MATLAB. And the next few lectures, what I'm going to do is take problems that we have seen in 2171 and solve them using MATLAB. Okay? So one of the things that people have observed is that the ratio of the composition in the vapor phase to the liquid phase is called the equilibrium ratio. Okay? And that is obtained experimentally. From experiments, you measure these K values. So you are given these K values, which tells you what fraction. If I know the fraction in the vapor, I can calculate the fraction in the liquid by simply using that equation, by knowing what K is. That comes from experiments. And in the feed, you know the feed rate and you know the feed composition. In this case, 5 numbers. So I'm going to take numbers like 0.2 for each. So that means it's an equimolar mixture, 0.2 moles of propane, butane, pentane, hexane, heptane, equal moles. And Ki, I'm going to give you a set of values. We'll just make up some numbers for that. Okay, maybe 5, 4, 2.5, 1, and 0.5, something like this. These are the K values for each one of the components. There are 5 components. You see why matrix MATLAB is a nice environment for this, because we are dealing naturally with vectors. Composition is a vector. I have 5 components. In another case, I may have 20 components. Okay? The same program would work, whether I have 5 components or whether I have 20 components. As long as I have the data for the feed composition and the data for the equilibrium ratio Ki. And we are going to define psi as the fraction of feed that goes to the vapor. Okay? So psi is defined as the flow rate V, the vapor flow rate, divided by F. So if psi is 1, what does it mean? All the feed goes to the vapor. That means I'm heating it so much, I'm evaporating all of them. I'm not really achieving any separation. You don't want to do that in a column operation. Similarly, if all the feed goes to the liquid, then psi will be 0. Okay? So I'm just asking you to be a chemical engineer, kind of projecting what it should be. Okay? So that again is not a good idea, because I'm not achieving any separation. The idea in the column is I want to get the more volatile material. C3 is more volatile than C7. What do I mean by that? It boils at a lower temperature. So if I maintain a constant temperature, C3, more of C3 will find itself in the vapor and less in the liquid because it's more volatile. Whereas C7 likes to be in the liquid phase. So the more of it will be in the liquid phase. Until if I increase the temperature above the boiling point C7, what would happen? All of it will be in the vapor. Okay? So if I adjust the temperature so that it is below the boiling point of C3, then all of it will be in the liquid. So each one has a boiling point, and I want to adjust the boiling point in such a way some of the lighter material goes to the vapor and the heavier material comes to the. That's a separation unit. And a multi-component distillation column is an extension of this, where you feed the crude and you adjust the temperature in the column such a way that you get different products: gasoline, aviation fuel, diesel fuel, etc. That's the basic idea of modeling a separation process. In this particular case, we are told that the equation that governs this separation is given by this function, which is a function of psi, and which is given by summation of I need to look at the equation because I don't remember it. Let me see whether I have it here. There it is. 1 minus ki zi divided by ki minus 1. Okay, 1 minus ki zi divided by ki minus 1 psi plus 1, I think. Okay, plus 1 equal to 0. So this is the equation that determines what fraction of feed is in the vapor. That is, it determines what psi is. In this equation, k is all known and z is all known. These are two sets of numbers that you must be given. What is the feed composition and what are the equilibrium ratios coming from experiments or from thermodynamic model. So you need to find that value of psi that makes that function equal to 0. Okay? What does that mean? Find that value of psi that makes that function equal to 0. Solve that equation for psi. In this particular case, it's a highly nonlinear equation, so we cannot really separate psi out and push everything else to the right-hand side to get an analytical result. So you must solve it numerically. Okay? And MATLAB has tools for solving equations of this type. A single equation, which is a function of single variable. Now, let's understand what we mean by solve this equation. Solve this equation simply means generate a plot of this function f against psi. Psi going from 0 to 1, because that's the only range that we are interested in. Psi is a vapor fraction, so from a physical point of view, if it is 0, it is liquid. If it is 1, if it is vapor. If it is somewhere in between, it's part liquid, part vapor. It cannot be greater than 1, cannot be less than 0. We have formulated the problem in such a way. So what we need to do is, given k and z, we need to construct a function. This is exactly what you're doing in your fourth problem in your assignment, to generate these function values. So take psi. In MATLAB, I will write it as psi. Okay, it's a Greek symbol pronounced as psi. Okay, and I'm going to say this goes from 0 in steps of 0.1 to 1. So I create a vector, and I pass this to a function that I'm going to write in MATLAB. Okay, and that function must calculate this entire thing and return that value. Okay, and then I can plot. So for example, when psi is 0, the function is somewhere here. The function value turns out to be that number. The function is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, something like this. So you have a curve. You can graph that function f of psi. Are you following me so far? How many of you are lost? If you are, please tell me. You are lost? If you're lost, just give me some hint. Like, what is it that you don't understand, and I can repeat it or come at it a different way. How many of you don't have a clue of what I'm talking about? Just say repeat it. I will try to repeat it. You guys are okay? You understand? Okay. So the general problem is any process unit that you're going to study as a chemical engineer will have an equation like this, which comes from mass balance, energy balance, which is what you are learning in 2171, how to write these mass balance and energy balances. Okay? And once you get an equation like this, a nonlinear equation, you cannot solve it by hand. 2171, you develop simple problems where you have linear equations you can separate and solve for it. But here you cannot. You must use MATLAB, okay? Or any other computer to solve this problem. But solving this problem means finding that value of psi where that function is equal to 0. So you generate a whole series of values of psi and then see where that intersects the x-axis. And that is your solution. Meaning if you put that value of psi in here, that function will be exactly equal to 0. Okay? So you can graph that and look approximately where that is. Or MATLAB has a function called fsolve, and that's what we are going to learn today. It's very much like fmin search. So if you understand how fsolve works, you will be able to use how fmin search works in a similar problem that I've asked you to do in assignment 4. Okay? So are we ready to go to MATLAB? I set up the problem. Do you understand what we need to do? We need to write a function which will take psi as the input argument and return the function value. So it's going to be something like this. Function f is equal to, I will give it some name. For example, distill. It's a distillation problem. And it takes psi as the input. So it takes psi as the input. And it must calculate this and return the function value f. And then I can plot one against the other. Or I can use it with other programs like fsolve to actually find precisely what value of psi makes the function equal to 0. So those of you among you who have good memory, remember this equation, because when I'm going to write it, I want you to kind of help me. So I'm going to go to MATLAB. I have already written the function. Do you want me to just open up the function, or do you want me to write it from scratch? Which one would be more helpful? That's good. That's good. I want to set up my path so that I am in the right lecture. There is a function called distill. I will delete it. Okay, so we will start from scratch, and we will make mistakes, and you'll have to help me fix the mistake. So how do I start? I say edit distl.m. You can put a .m. You don't have to put a .m. It will automatically put it for you. Okay. So when you do that, it opens up a new window and it says, okay, I'm ready to accept your definition, whatever the function that you're going to define. My computer is getting very slow even for these little things. Does not exist. Do you want to create? Yes, I want to create it. There it is. Okay. Now this is an important screen. There are a lot of other tools in here that I'm going to tell you, but this is the editor, MATLAB Editor. Okay. So I'm going to write the function f equal distill. This is the name of the function I give, and I call the variable as psi. You can give it any name you want. I'm just giving it as psi. Okay. And then the function itself I'm going to write. I'm going to write it in such a way that I want to calculate that function for every value of psi that comes in. So the psi could be a vector. Maybe let's do it for a scalar first and then extend it for a vector so that you see how the progression goes. Okay. So how would I write this function? F is equal to sum, because I have a summation. Do you remember that function? I need to kind of switch back and forth between these. Okay. Summation, there is a summation there, and in MATLAB that is sum. So that sum will take a vector of elements, calculate them, and add all the elements in that vector. Okay. So if you don't understand it, ask me. I'll go and explain it at a lower level by actually doing it on the MATLAB window. Okay. So sum, and I have 1 minus k dot star z. Any questions? If you don't understand, ask y dot, y z. Okay. All I'm trying to do is copy that function that is given to me. Okay. Divide. Should I have a dot divide? I should have a dot divide, and I will explain that why. Okay. And then I need to put the terms in the denominator, and in the denominator I have ki minus 1 psi, k minus 1 dot psi plus 1, and are my parentheses matched? If it is not matched, it tells you there is a red underline, right? That says that it is not matched. Okay. So in the numerator, for example, I have k 1 minus k dot z. So precedence ordering. You need to remember all these things. You need to internalize that. So what it is going to do is it's going to take 1 minus k. It's in parentheses. It's going to calculate that, and then k is a vector. So that will be a vector. If there are 5 numbers, 1 minus k will also have 5 numbers. That is multiplied element by z. Z also must have the same number of 5 elements. Okay? And the product is kept in the numerator. Then I need to go and evaluate the denominator. The denominator, I have k minus 1. So I need to evaluate the denominator separately. So I'm putting the parentheses. Now, when you take this, it tells you that these two parentheses are matched by putting an underscore there. Watch that. Are you able to watch that on the back? Okay. Times psi plus 1. So that is matching the entire denominator. Okay. So the denominator will be calculated, but I need still 1 to match the sum. Okay. So because sum is a function that takes a vector and adds it up. Now, if you don't understand any of these things, you can do this piece by piece. Okay? Would you like me to do it piece by piece? Okay? So, let me define these variables. I need them as global, k and z. So, I'm going to define 2 variables, k and z. They're declared as global variables, meaning it will be available in every function that you declare them to be global. Then I define k as equal to 5, 4, 2.5, 1, 0.5. That's a vector containing 5 numbers, a row vector. Okay? Z is equal to 0.2, 0.2, 0.2, 0.2, 0.2. Oops. What did I do? I missed the brackets there. Okay? So I have these 2 vectors k and z. Okay? So I can do, for example, one of the terms that I had, 1 minus k dot star z. Just enter that and see what it does. Okay? You can even do this, 1 minus k, what would it do? It will subtract k from 1. It returns a new vector, right? And then you can say that I'm going to multiply it with z. Okay? That gives you the numerator. Again, 5 elements. Do you understand that? And in the denominator, I have k minus 1 times psi. Psi is a variable, so I'm going to, for example, put here 0.5. If psi were 0.5, multiply 0.5 plus 1. Okay? So what I'm doing in the denominator is k minus 1 multiplied by psi plus 1. That entire term, if psi were 0.5, that's what these numbers would be. Now I'm dividing one by the other. I have 2 vectors in the workspace, but in this case they have been overwritten because if I'm not assigning it to any variable, it's stored in A and S. Okay? So I don't have numerator separately and denominator separately. But I can put them together. Okay? So I can write f as equal to, what did I have? 1 minus k, 1 minus k, dot star z, dot divide.
Why
Okay.
is it dot star?
Dot star. Why is it dot star? Please, I think it's important that you ask these questions. Okay. Why dot star? Because 1 minus k is a vector and z is a vector. So I want an element by element product in the numerator. So the dot star says do an element by element multiplication between this vector and this vector. Okay. Yeah.
Why do you have the dot behind the parentheses before the body in like your other window?
Which window are you talking about?
Like our original formula we got, we had a dot before the divide. In our editor.
Oh, in the editor?
Yeah.
Yeah.
You've got divide.
Let me open the editor so that I have basically the same thing. 1 minus k dot star z, right?
We have another dot. What is it?
Dot divide. Yeah, why the dot divide? I must have the dot divide. If I don't have it in the other place, it's a mistake. Why? Because the entire numerator is a vector. And the denominator is also a vector. So I want to divide every element in the numerator by a corresponding element in the denominator. So what I showed you in the calculation was numerator, when I enter 1 minus k dot z, it gives me 5 numbers, taking those 2 variables. Similarly, when I enter the denominator k minus 1 times psi plus 1, it gives me 5 numbers. So I want to have element by element division. So I must put here a dot divide. Otherwise it's a mistake, right? That's what you mean. Did you have a question there? Yeah.
Do you need a dot in the denominator?
This dot?
For psi, aren't you getting dot psi?
For psi, because, yeah, that's a good question, very good question. You can put a dot there, it doesn't matter, but only when both operators on either side of an operator are vectors, you must have a dot. If one of them is a scalar, but in this case 0.5 is a scalar number, so that scalar number multiplies all the vectors. You don't need explicitly a dot. Good observation. Do you understand? Yeah.
When you are multiplying two vectors that have the same size,
Yeah.
they do have to be the same size.
When you're multiplying two vectors, they have to be the same size. Yeah. And particularly for element by element multiplication, they have to have the same size. Yeah. Any other question? This is good. Now I know what you guys are thinking. Okay, so that is my function. This is my function value when psi is 0.5. Now if I want to calculate this for 0.4, I just go back, recall, and calculate that. So every value of psi, I can calculate a function value. Okay. Now this function value is actually contains these 5 elements. So I need to pass this to sum. Okay. So sum this. Okay. So that is the function value when psi is 0.4. That is the function value when psi is 0.2, etc. It is this one that we need to capture. So by working on the workspace, you figure out how to construct that functions, how to put together. And then I need to go and transfer that into my function so that I don't have to retype this every time. So now you should understand every line there, right? What it does. So it is going to get a value of psi, and using that value of psi, it's going to calculate the function, and it's going to return that function. So this f must appear in both places. You must assign the calculated value to f, and f must appear in the return value. Now, in this function, k and z are not defined yet. So to get the value from the workspace, I need to put the command global kz. Then, whatever value I define in the workspace will automatically be picked up here. How do I know that? Can I verify that? And that's what we are going to do next, okay? Through this idea of a debugging. So I'll put this function and I will end it. Okay? So this function is going to be saved. Any questions on that function now? Yeah?
Wouldn't it work if you don't define K and Z as global variables in a function? You just did it in the workspace?
Okay, you can, that's a good question. When you have a question like that, test it out. We will test it out, okay? So there are a couple of ways of handling this. When you're writing a program, that's one part. There is no unique single way. You can do it in many ways. Here I'm trying to illustrate what global variable does. Okay, so your question is, if I take this out, so suppose I put a comment, that means it's not effective. Okay, then if I try to execute this from the workspace, will it work? So what does execution mean? Even that's a question I think in many of your mind. So now I have a function called distil in my directory. So if I say type distl, it lists that function. Okay, and in the workspace I have this variable k, I have this variable z. They are defined. Okay, so the way I call this function, I execute this function, is simply enter the function name, oops, distl, and then pass a value for psi. Very good. So if I say pass a value of 0.4, what's going to happen? Control is going to go from the workspace to that function in the file with a value of 0.4 for psi. And let's see what it does. Subscript indices must either be real positive integers or logicals. So,
change the Z array.
pardon me?
You change the name of the Z array.
Z array. Oh, did I do that? Oh my God. Thank you for noticing. I didn't even notice that.
You changed it when you clicked the workspace.
Okay. So now Z is available and K is available. Okay. K is there, Z is there. In the workspace. Now I want to calculate the value of the function when psi equal to 0.4. I've written the function. So this is how I would execute it. Name of the function and the input argument. So something is wrong in the function. What is wrong? How do I find out? Okay. So there is something called the debugging feature, which basically says if you go and edit it, the edit window has a lot of these things here. Okay. So this line you see here, those are all executable statements. So if I put a breakpoint, that is, I click on it, it should become red. Why did it not become red? Because it says there is an error in this function. Terminate statement with semicolon to suppress output. Okay. I don't want this to be printing out every time. That's fine. Still, it doesn't accept. If there is an error in your function, when you are trying to set up a breakpoint. Now, I should talk about what a breakpoint is. A breakpoint is a line that you identify in your function where you want the execution to stop. When it comes to execute that line, you want it to stop dead on its track so that you can come into this function and ask what values it has at that point. And then you can stop execution one line at a time. It's a very powerful tool. Most programming languages, C, C++, they all have it. But MATLAB has it in its simplest form. Okay? So I need to now figure out why it is not accepting. It may be because the variables are not defined. So let me take this for a moment, okay? And then see. No. Still. Scope of variable k is global. Changes to its value might span multiple load spaces. That's fine. K and z are declared as variable. Psi is used. F is used. Why would it not work?
Is it because distill is defined as a variable in the workspace?
Which one?
Distill. You named one of them distill in the workspace and you didn't delete it.
You guys are sharp. I didn't even know when I declared them. I think I probably typed it. Okay. So clear distill. Okay. Let's go back. Nope, that's not it. It's a good guess, but that's not it. Oh, I'm sorry, I didn't save the file, that's why. So I have to save the file before I can set up. So when it turns red, that means it's going to stop. Watch carefully what happens. I'm going to go to the workspace, and I have declared in my workspace the global values for k and z. They are defined. Okay. So I'm going to call this function with distill. This time, let me change the value to 0.6. Okay. When I enter, normally what would happen is the control will go to that function distill. It will execute the whole thing and print it out. Now, it goes to that line and it shows you a green arrow. It means it has not executed that line. It has come there and it has stopped. It has given you the option to look at what the various values are. So if you take the cursor to psi, it will tell you what is the value of psi inside that function. So psi here is called a local variable. It's known only inside. Z is a global variable. Those are its values. Just take the cursor near it and it tells you what the values are. So you know that you are passing the right values, you are using the right values. Okay? Do you understand that? Setting a breakpoint means you ask the execution to stop and control be turned over to you so that you can examine what is the status of the calculations. And then these are the icons that allow you to control the debugging mode. So if you look at the workspace itself, it says that you are in the debug mode with a prompt that has K in it. Okay? Oops, I think this is stopped recording. This is the second part of lecture 6. Something went wrong during the recording in the class. As we saw, the recording started winding down because I think I was running out of space or something. So I'm continuing the recording from my office to illustrate what we saw in the class actually about how to write script files and how to drive the program. So in the class we wrote a function called distill, which implements the multi-component flash equation in a very simple line. So it takes as input psi, which we saw as the unknown variable in the function, which represents the fraction of feed that is in the vapor. and k and z are two variables. K represents the equilibrium ratio and z represents the feed composition. Those are known, and we are going to assign these values in the workspace or in the script file and pass them as a global variable, just to illustrate what global variables are. And then line 3 is actually the line that executes that particular function. So k and z are vectors of the same length because they represent the number of components. The length of the vector is equal to the number of components. And psi in this case is just a scalar variable, and we will see variations on this, how to make it a vector later on. So this is the function that we can call and execute from the command line. Okay, so we can, for example, define k as equal to 3, 2, 1, 0.5, 0.2, a vector of length 5 representing components propane, butane, pentane, hexane, and heptane as an example. And Z is an equimolar composition, so I'm going to assign 0.2, 0.2, 0.2, 0.2, 0.2. Okay, so I can now execute that function that I have written. Let me just type that function first. Type distl. So it gives me the listing of the function. Now I could also capture everything that happens in a diary command for submission. So I can say diary assignment 4, for example. Give it some file name. Okay, so immediately it will create a file called A04 or whatever the name that you have given, and start recording whatever you're typing on the screen. For example, now I say type distil, so it not only types it on the screen but keeps a record of it in A04. Now if you try to open A04 now, it won't display it because it has opened the file and it is trying to write to it. You have to close the diary before you can see the copy of the contents. So once again, let me define what k is and what z is, so that I get a record of it in that A0 file. Okay, now to execute this, all I need to do is type distil, and I put a value of 0.4, for example. So what I'm saying is evaluate that multi-component function, I guess I have a typo there, with the value of psi of 0.4 and k and z being global. Of course, I must declare them as global in here also. So let me declare global kz. Okay. So now it should be picked up as a global variable in the function as well. So let me now execute this to 0.4. So what has happened? It has transferred the control to the function distil and executed it and returned the function value as minus 0.0048. Now let me illustrate how the debugging works. So I open this file. Whenever you see a line against a particular, this dash against a particular line, that says that's an executable line, you can set a breakpoint. What is a breakpoint? You just press the left mouse button there and it puts a red dot there. That indicates that when control comes into this function and execution goes to line 2, it will stop. It will not completely execute and return the value, but it will stop and pass the control back to us so that we can see what is actually happening. Okay, so now let me execute the same statement that I had before, distil at 0.4, and you will see that call was transferred to the function distil, but it has stopped executing. The arrow points out where it has stopped executing. So if I want to find, for example, what is the value of psi that I passed, I take the cursor near it and it shows that the value is 0.4. And the value of k, it's a global variable. Okay, so once to execute one line at a time, I use the step function here. So it has executed that. So now k has been defined and z has been defined. Okay, these were the values that were defined in the workspace and passed as a global variable. They were not passed as an argument to the function calling routine. Now if I ask for what is the value of f, it will not tell me because it hasn't executed line 3 yet. It stops before execution. Now if I want to execute it, I step one more. So now it has executed the function. So the function value is minus 0.0048. And basically it has parsed and executed this entire line and assigned the value of f to that. Now if I say execute the next line, it is ready to leave. At this stage, let's go and see what are the values that are available in the workspace. Okay, so k and z of course are global, and f is defined and psi is defined, and these are local variables. Psi is defined only inside. Psi was not defined in the workspace, and you will notice once we come back to the workspace, the value of psi will be wiped out and the value of f will be returned as an answer. And the fact that we are in the debug mode is indicated by the change in the prompt. So you have this k here that indicates that we are under debug control in some function. So you go back to that function and now execute the next line. At this stage, the control goes back to wherever this function was called from. In this case, it was the workspace, so it will go back to the workspace. So we are out of the workspace. Now let's go and see what is available in the workspace. As I told you, f and psi were local to that, so the moment you come out of it, they were erased. Those values are erased. But the function returns a variable, and that is stored in a and s. Now, you could do this. You could say g equal to this. So what would happen this time is the function will go through the same calculation and return a value of minus 0.0048, but it will be stored in g, and g will be considered as a global variable. Let's just do it one more time. Okay, so we are there again, and I'm executing these through lines, and of course I have the same value, right? And I come out, and there in the workspace I will have g as assigned as minus 0.0048, but psi and f are not there. But they will be there as long as I'm inside that function. Okay, let me show it one more time. So I'm inside this function. I have calculated psi and f. So if I go to the workspace, I will have f and psi as a variable. K and z are there because they are declared as global. So they will be available in every function that declares them as global. But f and psi are local variables. So it's very important that you understand the distinction between a local variable and a global variable. Inside the function, whatever variable that you create will be considered as a local variable, except for the set of variables that are passed as arguments or through global. Everything else will be erased as soon as you get out of the function. Okay? So now what we want to do is, we know that this function works, and we want to make calculations with this function. What kind of calculations we want to make? We want to maybe, for example, plot this function. So I create a vector of psi between 0 in steps of 0.05 to 1, and I put a semicolon so that I suppress it output, but I have defined psi. Psi is now in the workspace. It is defined as going from 0, 0.05, 0.1, 0.15, etc. Then I want to calculate the function value for each one of those psi values, because I want to plot one against the other. So I set up a for loop for I equal to 1 to as many elements that there are in psi. So I can say length of psi. Okay, so this is going to count how many elements are there in psi and set up the for loop for as many number of times. Now I have to define what this for function is. So fi, the function for each value of I, is going to be equal to distl psi I. So what this is going to do is, psi is a vector. Each time it comes through this loop, it will change the value of I. The first time I will be 1, so it will pick up psi 1, which will be 0. The second time psi I equal to 2, so psi 2 will be 0.05, and it will go. So we call this function repeatedly 21 times, and each time it returns the function, and we build a vector, new vector called f, which will have the same length. Again, I don't want the output, so I put the semicolon there, and I end that for loop. Okay. I guess I have a typo there because it's distl, so let me do this one more time, this time without the typo. Okay, and then end it. So the first time a call came here, it will have a psi value of 0, okay, and it stops there. Let me execute. Now this time the return goes to within the for loop, so f1 will be created inside that global workspace. Okay, so if I go to the global workspace, I will have, well, I'm still inside the local variable because it has come in next time with the value of I equal to 2. Okay, so I need to go back to the function and ask what would be psi. It will be 0.05 because it has come the second time in the loop. Okay, so it's going to go out, and the control goes back to the workspace, but immediately the for loop sends it with the next value. Okay, now psi 3 will be 0.1, so it is 0.1. Okay, and in the workspace it will be building this array with f1, f2, f3, etc. But we are not stopping in the workspace, so it comes back. The control comes back here. Okay, so it's working fine. So let me take the breakpoint so that I don't stop every time and then say continue. So this time it just goes back 21 times between the workspace and this function. And in the workspace, I will have a new vector f, which will be same length 21, and that will have the function value. Okay. Then I can say plot psi versus f. Sorry, psi versus f. Okay. So it'll generate the plot. Okay, and you can see the plot is like this. And what we really want to do is find that value of psi where the function is equal to 0. The function 0 is here. So somewhere around 0.4 is the actual solution. That is, the vapor fraction is when it is around 0.4, the function will be close to 0. We'll see how to get that exact value. Okay, but now we know how to plot this function. Okay, so let me, instead of typing everything from the command line, let me show you something called a script file where you can put all these commands. So here in the history, you will notice that I have these commands that I have entered. A copy of these commands are kept, right? This one and this one that defines it. So I'm going to take all this and highlight them and then right click it and say create the script. Okay, so it creates a script file with all the commands that I tested in the workspace that work, I know. Okay, so now this is a script file and I can give it a name. So I will save as in the same directory as maybe test1.m. Okay, it's a new script. Now this is not a function file, so the first line doesn't start with the function keyword. It's a script file. Script file contains any commands that you can normally enter from a workspace, input it here, and then just type the name of that function. It'll execute as if it is being entered from the command line. So the first line defines what psi is, the second line sets up, second, third, fourth line sets up the loop, and the fifth line plots it. So I'll show you another feature of this. If you put, you can put any comment, okay? But with the comment, if you put double percentage, it creates something called a cell. So you can say part 1 plotting demo, okay? And you end that with a single, and then you create, for example, a second cell, okay, solving for psi. So here there is a function called fsolve, which takes the name of the function, distl, and takes an initial guess and tries to find that value of psi that will make that function equal to 0. So fsolve is a built-in function in MATLAB for solving nonlinear algebraic equations. Okay, and the structure of solving any problem like the fmin search that you're going to use in your current assignment will be the same. So you have to tell fsolve which problem you are solving. So you need to define that function by writing your own function. In our case, it's the function distal, and it has as input psi. So you give in a guess of 0.5. And what fsolve will do is will send a value of 0.5 to distal and say, tell me what is the function value. And distal will return a value, something like minus 0.1. Then fsolve says, okay, that is not the psi value that's going to make it 0. And then the next time it gives you a different value, maybe 0.4. And distal has to return what the value is. So there's a search process going between fsolve and distal. And the distal's job is, whenever it receives a value of psi, it should return the function value, and fsolve will then, using its intelligence, will find that value of psi that makes it equal to 0. So we can, for example, solve this in psi solution, a new variable that you create. Okay, so this is a script file. Now I have divided this into cells by simply putting these 2% signs. Okay, this 2% sign starts saying that is the starting of a cell. The idea of a cell is that you can execute only those lines. In a script file, you will see this green arrow that says execute that. Okay, so if I press that, it's going to execute line number 8 and 9, that is the second cell, and it would have executed it, and you would see the result in your workspace. So it is as if these commands are entered from the workspace. Okay, so here you see equation solved, and it gives you some information from fsolve saying that I have found the solution. What is the solution? The solution is actually saved in a variable called psi solution that's in the workspace, and the actual value is 0.4068. Okay, I give an initial guess of 0.5, but it returned the value of 0.4068. Now, how do I know that this is really the solution? I can evaluate the function using that value. Okay, what should I get now? I should get a value close to 0. So it is 10 to the minus 7. Okay, so that is what the tolerance is. So inside, by default, fsol is set such that it will find the results to about 7 significant digits. So the error in the function is of the order of 10 to the minus 7. So the result that you have found is accurate to about 7 significant digits. Okay, let's go back to the script file. Okay, now we can set up the breakpoint in the script file too. Okay, so suppose I set up the breakpoint here, and then I am in the first cell, or first cell, and I start executing. So it stops at the line number 3, and right now we can ask the question, what is psi? Psi, of course, was defined from the previous time. So maybe let's go to the workspace and clear the workspace of all the variables. Okay, so everything is done. Now if I go to the script is now, remember, we have erased also K and L, so I need to put in the script file global K and Z, and I need to define what those values are in the script file. That was 3210.5, 0.2, and Z as equal to, let's try a different value, 0. Well, let's try the same thing, 0.2, 0.2, 0.2, 0.2. Okay, so I need to save this. Okay, and when I save this, of course, I abandon the execution. So now I start the execution again. So it's line 3, I execute once, psi is now defined. But is K defined? No. Is Z defined? No, because that line hasn't been executed. Now we have declared K and Z as global, but we have not still defined what K is. That, I guess it's there. So K and Z are now defined. Okay, now the control is going to go to distill many times. I want to show you how the for loop actually works under debug control. So I step it, so the value of I is going to be equal to 1. Okay, psi actually has 21 values, but psi 1 is going to be 0. Okay, so now the control has gone to distill, and the value has come. So f will be of length 1, and its value is minus 0.34 when psi is equal to 0. Okay, so let's go to distill and set a breakpoint there also. Okay, and then so I'm showing that you can set up breakpoints in different functions. So what is happening is control is going from the script file this time to the distill function. Okay, so now it's asking at the end of the loop, have I finished? Is I greater than the length of psi? The length of psi would be 21, so it is not. So it's going to come back. This time I will be 2. Okay, and the control this time will go to distill, but it will stop there. So what is the value of psi? 0.05. Okay, and it comes out. Control goes back to the script file, because this time we call it from the script file. Okay, so it's at the end of the for loop, and it's going to go one more time. Now this time I will be equal to 3. So it's very good for testing as you are developing the program. And f will have a length of 2. There will be 2 numbers, but f3 hasn't been calculated yet. If I do this one more time, now I go back to the distill function and return back, and this time f will have 3 values because I have completed the loop for 3 times. I is equal to 3. Okay, you get the idea. Now let me go to this and remove the breakpoint and come back, and then just go through this loop as many times as you can. See, just going back until it finishes 21 times, because it knows the length of psi as 21. Okay, so if you look at I right now is 10. It has done 10 times, so f will be 9. The 10th time it's going to execute right now. Okay, and so you can say, okay, continue this. Instead of stepping it, just continue, and it finishes the whole thing and generates a plot. But it executes only the first cell, so the plot would have been generated there. Okay, so you can do this cell by cell. Now I told you about the diary command. There is another way that you can create a report. It's called the report. Okay, and here it is. So if you press this, okay, it says edit publishing configurations. Okay, so you can go here and say generate the whole output as a report, but produce it as a PDF file, for example. Okay, so click here and select PDF as the output. Okay, and publish. So what this does is it runs through the script file, executes every command, and the output is captured in a nice single file as a report. Okay, so this is better than actually using the diary command, and I will show you how the output will look. Okay, it's still executing. Okay, there is your test1.pdf. Test1 was our script file name. Okay, so here it is. It says part 1, plotting the demo, and these are actual commands that were in the script file, and this is the output that is produced, a graph. It also produces the graph and puts a copy of it. And then the second part of it, solving for psi, and this is the command that we used, and the output is equation is solved, fsolve completed, and if we had put any fprintf command, it will print that also. For example, let me go to this function in the script file. Okay, close that. Close that. And go to the MATLAB and go to the script file, and here after solving it I want to display the result. Okay, so I say fprintf comma solution is %g \n comma psi solution. Okay, and it says there is an error because I haven't closed that. Okay, there it is. Okay, so in the script file now I'm not only plotting it, I'm solving it, but I'm asking to print the solution. Okay, so I can go back here and then say publish that in PDF. So it's going to go through the same process again and produce a new PDF file overwriting the previous one. Maybe it will ask me whether you want to overwrite. No, I guess it didn't. It automatically overwrote that, and this time it has the output solution as 0.4607. So diary is one way of capturing what you have done, but this publishing report is another way that you can generate the report. Now what all we have done, I think, has been also saved, but the diary command saves only the interaction on the screen, the command window. It doesn't produce a copy of the graph, for example. Okay, so I say diary off. Okay, so it must be capturing all the mistakes that we did, everything that we did right from the beginning. A copy of it. Okay, you can go and edit this, but I prefer the other way as a better way, but whatever you want to use, that's fine. So that shows you the difference between local and global variables, how to write a script and drive a function to solve a problem, to plot, things like that. So let's stop there.